Speaking of bringing a team together, I should have thanked my teams for this lecture. Joe and Locke came from Paris last night, arrived quite late. Shaney came over from California to join us, and really appreciate your help in putting this thing together and doing this, this lecture. I'm going to talk about the Channel Tunnel because I spent a lot of time in France and England making what was really a very, very treacherous and very difficult project come through actually on the original schedule, having started late. But this shows that we have other geologic sections, but it was a 39-kilometer tunnel under the sea, and then there were sections of the tunnel under the cliffs on each end which were not under the sea. So our machines had to do this section here, both from the British side and the French side. In 1974, we built the first tunneling machine for a modern tunneling machine for the Channel Tunnel. This was an early double shield machine which used cast iron segments. It was all set to go. We had it at a portal on the French side, a French-German joint venture, and then the British decided that they couldn't afford to fund this, so the British government pulled the plug on the job. It would not be done. It was quite clear that the Channel Tunnel would not be built with either the French or the British governments putting any funds into it at all. So they let a contract in 1986. That's the Iron Lady, Margaret Thatcher, making an agreement with Francois Mitterrand to build this tunnel and accept the tunnel to be turned over from a private joint venture of British and French contractors, 5 on each side, that formed a company to provide all the financing. There was no guarantee that this tunnel would be a financial success. My 2 kids at one time had shares in this tunnel. All of the shareholders basically lost their entire investment. The contractors lost all their investment in this project. There were 115 big international banks that provided billions of dollars for this project in construction financing. They wrote off all of that, and so it was really not a financial success at all. But the government extended the term of ownership of the tunnel for the contractors, so they're gradually getting paid back and paying back some of the debt to the bankers. The design is just like it was in 1974 when we first started. 2 main running tunnels, one going east and the other going west. A service tunnel was in between, which, as I recall, is about 15 feet in diameter. Or was it 18 feet? And then crossovers, air tubes, pressure relief tubes, relieving the high-speed train pressure from one tube to the other, and then connections for emergency escape. In case you had a fire in a tunnel. The train would stop and the people would get out of the train and go into this service tunnel. So it was an escape route as well. That happened actually about 6 years after the tunnel was put into service. So this is the tunnels, 15 meters from the service tunnel in the center, with the cross passages and the piston relief duct over the top. The first machine we built was the 18-foot diameter service tunnel machine for the French side. And this was built in Seattle and in Portland. We finally assembled it in a factory in Portland so we could ship it from there. The pressurized, oops, go back to that. The blue section is under very, very high pressure. And this is fluid pressure, and it turns out it's sea pressure, because up here in the front and all around the outside was fractured chalk. This is the blue chalk, and the third layer down, that on the French side was directly connected to the seabed. So we had 10 bars of pressure of seawater that we had to figure out a way to, well, I'm hitting the wrong button again. We had to figure out a way to get the cut rock out of the tunnel and into atmospheric pressure, which is where the men are all working in this zone here. So we developed this pair of piston dischargers, like two great big concrete pumps, and we'd take the pressurized muck and water out here in a conveyor, a big screw that would, out here was about 10% solids, up in here was about 60% solids, and it would discharge it to atmospheric pressure right here. And it kept the tunnel sealed. Of course, we had here the end of the shield, which had to be sealed against the concrete segments, and these segments were all themselves sealed to keep any water from coming in. So this was a major sealing effort here. That's the front of the machine. Had disc cutters and drag picks. We were able, when we got further along in the tunnel, out of the gray chalk, middle chalk, to the blue chalk, we were able to operate with just drag picks. Moved ahead at a kilometer every month with this machine eventually. We had, oops, let me go back to that. We had probe drilling holes here. We had a gripper system here that would allow the machine to bore forward. At the same time, we were placing concrete segments during the good boring, but in the pressurized boring, we had to extend the machine with the machine standing still so they could seal it. This is the geology, and you can see over here on the French side, we had the upper chalk. These are the White Cliffs of Dover. We had to go through that kind of middle chalk into the blue chalk, which was a much more friendly material to be in, and stay in that formation throughout the tunneling, because it was impervious to water. So as a result, the tunnel had vertical curves all the way through and horizontal curves to stay in those conditions. So it was a really tricky surveying job, you can imagine, having two crossovers here and here, and the joint, the meeting point in the middle here, having the surveying so that the two tunnels, the two service tunnel machines that actually made the connection come together. And it was quite accurately done. This is the first running tunnel machine. It was 8.36 meters in diameter. That's 28 feet in diameter. And we built these machines with a different design than the French machines, because the British machines were going to be in that good blue chalk all the way. Their main concern was running into a survey hole which was drilled through the seabed, and they were concerned that they might encounter one that wasn't sealed. So it was capable, whoops, hit the wrong button again. All right, and this is the machines, two machines which were built in joint venture with the Robbins Company and Kawasaki. This machine was mainly built in Japan, although we shipped some parts of it from Seattle and from Europe. And another machine of this type was built in the north of France and assembled there. But these machines had the same features as the service tunnel machine from the French side. Here they're pumping in grout as backfill behind the tunneling machine on the service tunnel. And this is the main French running tunnel machine being set up in the starter tunnel from the French shaft. This is the sealed segments coming in. These segments were all with rubber gaskets so they would carry that water pressure and not leak. The French segments were not sealed. You can see that, I'm sorry, the British segments. This is placing the British segments directly against the blue chalk, and the propel cylinders here shoved against those segments to move the machine forward. Here's the connection of the two service tunnel machines. On the British side, they stopped 100 meters apart so that if there was misalignment, they could adjust the position of the machines. And they drilled a hole from the British tunnel head into the cutter head of the French tunneling machine, and that's it coming through. And then they left a little wall in between and dug it out by hand so they could have a big televised connection party. And they picked two guys, one French and one British, to dig the last little bit with this air spade, and they came through, and let me tell you, it was one heck of a party. They ended up, this is nearing completion, one of the British muck trains hauling muck back to the British side. This is a luncheon in a crossover on the French side with white tablecloths and candles. Margaret Thatcher, whoops, I'll back it up a little. Here, and that's me back there. Here's the Queen and Francois Mitterrand coming together. She came on that train behind her, and she had her Rolls Royce on the train with her. So it was quite a party. There's a little video here And I don't know whether there's
Should be sound too.
sound. How do you do that? Oh, okay. I guess that's me talking. And we were shipping the, oh, we can do it without sound.
Yeah, I don't know why it's not. It's worked for everything else.
Yeah. Anyway, we shipped this machine from Portland, and they made quite a big deal about the fact that my father, Jim Robbins, was a consultant for the earlier, one of the earlier attempts to make this job go forward, and visited the French tunnels, which were where the Beaumont machine had bored. And so I was able to go there and see those tunnels as well. The machine came through the Suez Canal, and it's being unloaded here. This is the first service tunnel machine. The crane that lowered this machine down the French shaft had to lower the the running tunnel machines, the Kawasaki Robbins machines, which weighed 450 tons, down a shaft that was something like 350 feet deep. And so you can imagine the equipment that was involved in this job. A lot of this is transporting the machine to the site. One of the interesting things about this was that the machine, the backup system, and the machine itself on the French side was designed to operate as a slurry tunneling machine in case we had to pump the muck out instead of working with the piston discharge system which we developed. It was the first time a concrete type pump with half-meter diameter pistons was built, and I must say there have been others like that, but much smaller since that time. So we spent a lot of time in the tunnel. Interesting thing about this job is that almost everything that could fail on this tunneling machine failed in the first 2 kilometers while we were in the very bad ground. This shows these features of the cutter head extending and the piston discharger operating, the grippers, the segments coming in over the top, being erected with these vacuum pickup systems to place the segments. This is very much like your standard slurry or EPB type machines. I think these may have been the first vacuum pickup, which was a question Shani asked her people in her news item, but that might have been the first one. So the French were managing this machine, which was started way behind schedule because we were late shipping it, and then everything on the machine broke, and we repaired everything in the tunnel piece by piece, electronics, the main screw and everything. We got further behind. We were about 9 months behind schedule And I made a bet with the contractor, the manager of the whole project, that we would finish this job on time. And if we didn't, I would take him and his top management team to the best Paris restaurant, which we had worked on for years before that. And if we finished on time, he'd take us. And he ended up taking us to dinner. It was quite an experience because the French managing director was decided to be laid off, and they didn't have anybody to replace him. So the project manager on the French side said, "Okay, Robbins, you have a chance to put your money where your mouth is. You're in charge." And he let us take our project manager, and he managed the entire French shaft from there all the way to the middle. And it was a mistake that we didn't put him in charge in the first place. But it was luck, because by that time, everything that could have failed had failed and been repaired, and the machine took off at that point. So it was one of those lucky deals. We were given a very, very substantial bonus to complete the job on time. And when we finished the job, we ended up with a big profit. But when we shipped the machine, the first machine, to Sangatte, to the French shores, we shipped it at just double what the amount of money that we contracted with them to pay us for it. So I bet the whole company on that job. And our bankers told me, "Well, you can make this one bet, but that's the end, and we're bailing out." And we had to get a new bank after that. So that's the video. I thought I would talk very briefly about other important jobs. This is the Paris RER Metro in 1963. This machine was the first machine with a pressure bulkhead, and this had the compressed air on the face that lit Paris on fire. And we were able to finish that job. Again, you can see sealed precast segments. There were other features you wouldn't believe. This machine, they built a ring of segments from bottom to top continuously. When the machine had moved forward far enough to start build again, it was ready to open. The segments on the bottom were advanced, as you can see here, one whole ring ahead of the ones on top. So the machine actually was a shielded machine that could move continuously forward. This is the Mangla Dam in Pakistan, 1962. This machine was 36 feet, 8 inches in diameter. The first continuous conveyor. In this machine, the muck was all taken continuously out of the tunnel for the first time. The same machine we took and shipped from Pakistan to the Mersey River, and this is the next successful tunneling machine. They put a little pilot tunnel through first, and then the machine was used as a reamer to ream out that pilot tunnel. And talk about small diameter, here's a 4-foot diameter tunnel in South Africa. This was one of the, a box hole drill. So it gives you an idea of how small some of these machines, hard rock machines, can be. These are machines that didn't work. Here's the first walking gripper machine that was designed to walk itself continuously down the tunnel. Whoops, I keep hitting the wrong button here. These shoes, every other one would grip and shove and then relax and go forward and grip and shove while the other one was moving forward. We didn't have the electronics and we didn't have the hydraulics and the valving systems in those days to allow this to happen. Today it's my hope that we will make this type of machine succeed. That was a little 7-foot machine. The Germans built a similar machine with walking grippers. This one did succeed, but it was the only one they ever built. And so the advantage really wasn't there. Here's a hard rock tunneling machine boring a granite tunnel. In fact, it was a 7-foot diameter remake of that first little walking gripper machine. And we used high pressure water jets, 60,000 psi. You can imagine 400 bars to cut granite. There you can see the water jets here, the array of jets. And the idea was that the jets are supposed to make grooves in the rock that the disc cutters would break the rock into. But the disc cutters worked a lot faster than the jets, so it really, whoops, I did that again. This was a German version of the same thing and built in 1978. They didn't follow up on it either. The next issue was making non-circular tunnels for underground mining. And this is soft ground, a very powerful double road header for making a non-circular tunnel. And this was coal mine tunnels in England. And that's certainly something you can do with this type of cutters in soft ground. In hard rock, you just simply can't do that. So we invented a new type of machine with the cutters just on the periphery of the head and arms that swing back and forth that allow you to cut a tunnel of this shape. This is Mount Isa Mines in Australia. Very, very hard quartzitic rock. And you can see we did quite a bit of tunneling. This is also in Mount Isa. This was at the Pasminco mine in Australia. In this case, our customers, these two mining companies, each spent about $25 or $30 million on these developments. The Robbins Company spent almost that much as well, and we still have not produced a machine that can do this kind of non-circular tunneling as fast as you can drill and blast it. So you can see that there's a big scope for future tunneling in underground mining. There's more excavation in underground mines than there is in all of our civil engineering work. So there's a huge scope for the future of tunneling. And this is a machine we built for a Taisei company in Japan, and it's the same kind of a mobile miner, but a ranging head, which they built a highway tunnel in Japan with that machine. And there it is in the tunnel. So this is another non-circular machine, which was built by the Jarva Company in Ohio, and they were cutting the bottom of, reconditioning the bottom of slope tunnels in coal mines here in the United States, eastern United States. So technically challenging. I'm going to run through these really quickly. Mud. This is a job in Melbourne, Australia. The running mud that would inundate the. This was before we had either EPV or slurry type machines, which is what you'd have to use today. Here's a tunnel in Austria. This is water coming in over the top of the machine, coming in through the walls, and you can see ring beams here, but there were places it just poured in. There's water under very, very high pressure coming in. As you can see, it dumped a lot of rock on the machine. And some places it's just a river. Somewhere I have a slide where the guy's in an inflatable boat moving around repairing parts of the machine. So where are we going from here in the future? There are many concepts. One of the problems, it's like this job in the Andes, you're tunneling under cover that's sometimes 2 to 2.5 kilometers under the top of one of these mountains. And the rock pressure and rock temperature is so high that the pressure is greater than the strength of the rock to support it. And so you get rock burst like the deep mines in South Africa, where the very, very hard rock fails with rock burst. It's like a underground earthquake, and very, very dangerous condition. So when the rock in the ground is not so hard, it actually squeezes. And we see that happening in a lot of tunnels in the Alps. So you needed to have a concept that can convert from a standard machine here, open gripper type machine, to one that will handle squeezing conditions. There are several different concepts in this one machine, but you can convert it to an open machine which uses wire mesh, rock bolts, shotcrete right up at the face, even filling holes in the face ahead of the machine. You can have a walking blade, continuous advancing machine that will allow the outside of the shield to actually get smaller as the ground squeezes it. And the same thing can happen with lower pressure conditions with a gripper system working on the inside of precast segments. So this is the open top tunneling machine, and the low pressure or the high pressure walking blade shield that allows the ground to just get gradually smaller as you put in yielding type of segments. And that's what such a machine would look like from the rock's perspective, one that will actually handle squeezing ground. Now this won't handle those big water flows, so we haven't figured that out yet. There's a lot of room for doing new things still that we haven't done in mechanized tunneling. So there's a breakthrough, and that's the end of our lecture. We want to thank you all for being a rather cool temperature here. So if you have any questions, one of those clients is a joint venture group that, well, in fact, there's 2 or 3 that I'm aware of, that some of the contractor customers of ours have said, we're just not going to bid that job. We know that we're going to get into big disputes with the owner of the job, or their consultants who designed it. So that's a job that we're just not going to participate in. That's a serious problem, and the big tunnel that's going to come along now in Seattle is of a size and conditions that we think there may be only 1 or 2 bidding joint ventures for that job, and maybe 3 potential suppliers of the tunneling machines. So right there, you're digging yourself a hole. If they could have made that a pair of much smaller tunnels, they would have found also better geology, and you would have had all kinds of manufacturers of machines and contractors bidding the job. So a lot of it is a political issue.
Jerry, you have a question?
Yeah,
Oh,
probably real quick.
go ahead, Jerry.
Vic, the things that broke on the channel board, did you redesign and then fix, or did you just fix as it was designed?
No, we redesigned some of those features, but a lot of it was, for example, sealing for the electronics was not properly sealed, and we got seawater coming down and getting into the electronic systems. We had the main screw conveyor actually fail, and we had to pull it out and replace it with a spare. We did do some modifications in the tunnel, and in many jobs, you know, these are custom designed, custom built machines. They're designed for the job for which the contractor bids, and sometimes the geology doesn't suit the machine. We could go so far as to say that very large machine in the picture right there, which is an open gripper machine, should have been built either as a double shield or a single shield machine, because the geology was a lot less stable and a lot more water than they anticipated when they bid that job. It turns out they're getting the job done, but they're modifying the backup system, they're modifying the machine, they're modifying the support systems as they go. So there's a lot of, I would say, multidisciplinary engineering going on in the tunnel with electronics people, with a lot of sort of R&D work to fix these things as you go.
Are there any more questions? Yes, sir.
The smooth cutter wheels that you use in hard rock, when I have to drill through rock or cement, you use a hammer drill and you get the hammering plus the cutting. With some sort of eccentric cutter wheel or something that could hammer the rock a little?
We did make a drawing of such a machine. You know how rock crushers, there's a type of rock crusher which is a hammer crusher. It spins with arms centrifugally held out, and you drop rock in and it just fractures it because of failure. Well, we drew a design of a machine with an arm with one of those on the end of it, and we got some very amusing cartoons imagining the chips flying off of that machine. But frankly, the machine that we built for the Australians, those 2 different mines, was almost like that, because these cutters would come around and enter the rock so quickly it was like almost like hammering. We did work with a German researcher on providing vibration through the cutters into the rock, and you could increase the peak loads in the rock that way and break very brittle rock that way. but the cutters got the same abuse. And so the cutters couldn't be designed that would handle those conditions.
Follow up the vibration, I've used what they call sonic drilling, where it looks like a rock core barrel, but it vibrates at a high frequency. And we move core in landfills through railroad ties,
Yes.
engine
Yeah.
blocks, and it's... that
We
vibration-
did build such a machine. We made a conventional shield with a backhoe, and we hooked a very, very high-powered vibrator on the thing to see if we could cut into hard rock. And if you can't get rid of the chips, you can't make blocks. And so that didn't work either. But we turned an awful lot of steel into molten material, pushing it against hard rock. Yeah, indeed.
Well, I'd like to thank the Robbins people for coming and sharing some of their technical expertise with us. I also would like to thank Villanova University in the person of Professor Jerry Jones for their hospitality for this presentation. Tonight we will be awarding a medal to Mr. Robbins at the Franklin Institute, and this is all part of the same celebration. Thank you all, and I wish you well.